Hello, I'm Evan. I'll be doing question 1. So for this problem, we are given a moment and we are trying to find a force, and we are also given these two directions. And so with those two, we can solve for the hypotenuse, which is what we're going to use as the radius. And so with that, we can use this formula where moment is equal to the cross product of radius and force. And all we have to do from there is take the moment that we were given and then divide it by the radius that we just calculated with Pythagorean theorem, and that'll give us a force of 8.885 pounds. And then in order to find the angle of it, all we have to do is take the inverse tan of the same triangle that we did Pythagorean theorem on. So 8 would be our opposite, 22 would be our adjacent, and then we just plug it in and you would get 19.98 degrees.
Can you explain like the angle part of it?
Like the geometric angle calculation, because that's a little, it's a little geometrically.
What we plugged in,
So how do you know that? How do you know that this angle is the same as that?
So my thought process is that this would add up from this normal angle, like this is 90 and this is 90, and so it's either complementary or self-memory. I'm not sure what the word is for it, but these two have to be, in order for that to work out and each be 90, these two have to equal each other and these two have to be equal to each other.
Oh, so you just solve for this one, that's this one.
Yeah.
Okay, that makes sense. All right.
How's the lighting? Okay, there we go. Okay, I'm Andrew. This is problem 2 we're going to lead the discussion on. So on this problem, we're given a force on point C, and we're trying to find the perpendicular distance from point A. So this problem's a little bit different because you're not actually calculating for the moment, so I think that kind of throws you off at the beginning. But you still do need to calculate the moment in order to get this perpendicular distance. So we know the moment at point A is equal to r cross f, which is kind of what Evan was just talking about. And we can relate that to the moment at A is equal to the force times the perpendicular distance. So once you solve for the moment, using just the vectorization of the force and the vector of AC, and then just do the cross product right here, you're going to get a magnitude, and we can plug that into this equation and using our given force, and we're going to have the perpendicular distance.
Can you just explain how r cross f equals f cross f?
Okay, yeah. So this is the radius and then the force. So the radius is going to be the same thing as AC, so that's what we're looking at. If we're calculating it with respect to point A, and the force is at point C, so that's going to be the radius.
Oh, I see.
And then force at point C is going to be what we're given, so we can just use the magnitudes of that, the vectorization of that in the cross product.
That makes sense.
Yeah. All right, we good? Thank you.
Hi, class.
Here, we need a, let me get that.
I threw it dramatically.
It's right there.
Does this look good?
Yeah, sure. I'm Thomas Brandt. This is question 3. So basically, we're given this diagram, and we want to solve for theta. At first glance, you'll think, oh, I can do that with triangles and angles. Don't do that. All right, we're gonna use this equation. We got AB, this vector, dot product AC, this vector, and then is equal to the magnitude of AB times the magnitude of AC times cosine theta, and this is the theta we're solving for. So first, you wanna turn your vectors into. You want to take the point and write out the vector in the IJK format. So we did that here for AB and then AC. Then I took the magnitude of them. And then for the dot product, we're looking back here. And so we're multiplying the I component and then adding it to the multiplication of the Y component and then the Z component. We'll get that number. And then we just plug them all in. And then just like that, we get 38.719 degrees, which is this.
I do have a question. No questions?
There you go.
Okay,
Lay it
so
on me.
the way you're originally doing it, is it just quicker to do it this way with the dot products, or is it like you can't, like it just wouldn't work out?
If so, we went through this kind of similarly with the masked problem in the one of the previous homeworks. I think in theory it is possible to actually solve it with triangles and angles, but you don't want to do that, and we should use what we learned in lecture. Another thing Andrew was walking me through this earlier. Remember the error I made? Do you remember that?
The negative?
Yeah. So I got the wrong answer originally, and I was scratching my head. How did that happen? It's because
The 12 and the 24. So the key is, I think the 24 was in the negative z direction.
yeah.
And so I think when you were doing the cross product, you had a switcheroonie there.
Yeah, so when you define which way is positive and negative on your axes, and make sure you're consistent with that. And because when you do magnitude, it doesn't matter because it's being squared and all that. But with dot product, it does matter. So make sure you remember those negatives.
I think the key is consistency. So like as you can see, Thomas has his like this is his z positive, his x positive. So you could like reverse it if you really wanted to, but I think usually like just be consistent and you'll be fine.
Thank you.
I think it's
Alright.
fine.
I'm Case Rowan, and this is problem 4. So we have some frame ACD and a tension BH. There's also BG, but we don't have to worry about that. And we're looking about the moment of the tension BH around the length AD. So we have this equation up here, which is the moment is the perpendicular distance to the force, which is actually RAB, like the distance A to B. But then we need to dot product that with the unit vector AD because we're looking at the moment about that kind of distance. So our first step is to look at the direction of the force, like the XYZ components of the force.
To get unit vectors.
Yeah, we want the unit vectors of the force because it's not like perfectly perpendicular to it. So we get the vector BH and we divide that by the magnitude and we get the direction, and multiplying that by the actual force we get, which mine was 700.
The given force.
Yeah. We get the actual components of that force BH, of that tension BH, sorry. And so now that we have that, we want to look at the unit vector AD, which is actually the direction we're going around. And we have the components, 1, 0, negative 7.75, and then we just divide that by the magnitude, and we get our unit vector. And then plugging in all that stuff we just got, we have, oh, and sorry, I forgot to write it down. We know that RAB is just 0.5, and it doesn't have a J or K component. So plugging in those 3 values, we take...
Do you need to unit vector this, or is that just like...
No,
just
'cause
the distance?
That's just the perpendicular distance.
Okay.
So we just plug those values in, and the I and the J components just go to 0. So
So that's not a vector, that's a distance. I see.
Yeah.
Okay, yeah.
But we turn it into a vector just with one component. And then we end up with a negative moment, which is negative 140 Newton meters.
Okay, I think the key that when I was approaching it was I was looking at, so like it's rotating around the axis like AD. Like this whole thing is kind of like rotating like that.
Yeah, it's kind of hard to visualize.
Do you have to like do this distance as 0.5? Because I was trying to think I could calculate this distance because that was the axis of rotation. So how did you know to do it like with respect to point A? I don't know if that's like...
I
also was confused by that.
I was looking at it because we need the perpendicular distance to that force. And since we're given that force, like the...
These are perpendicular, I guess, right?
Yeah.
Oh, okay.
And then...
Oh, because this would not be perpendicular. This would be...
Yeah, that wouldn't be... That's what I tried that first, too.
Okay. That actually, no, because I was trying to do this, and this was like 0.3 or something.
Yeah.
It was really
The
weird.
trickiest part was like this, like kind of getting the components of the force. And then,
Yeah.
But that's it.
Yes.
This guy's a genius.
Thank you.
All right.
All right.
Oh, there we go.
Thank you.
We had a crowd this time. Hello to the random people watching our YouTube videos.
Hi, guys.
Like and subscribe.
Yeah, this is statics and dynamics, if you're curious.
This is homework 3. Get ready for homework 4.
This is
It's coming soon.
Stay
All right.
tuned.
Bye, guys.